So it seems that we're ready to go. Okay, so let me start saying many thanks to all of you for attending this meeting. On behalf of the scientific and organizing committees, I would like to welcome all of you to this 3 days event, which we have organized to celebrate the 16th birthday of Enrique Zuazua, who I am seeing him among the participants. Hi, Enrique, morning, how are you? Or good afternoon for you. It is morning for us, but afternoon for you. Enrique is a very close friend for more than 35 years. We are very proud of him and of his career, throughout which he has enriched mathematics with all what this such a statement can mean. So you can easily imagine how happy we are to celebrate his birthday from the Chilean community of applied mathematicians, where he is considered a member of our family. So very welcome, Enrique, and everybody. The meeting is organized around nonlinear theory and control theory. Nonlinear analysis and control theory, which subjects in which Enrique has contributed with seminal ideas and with extremely fruitful collaborations with colleagues all over the world. For this opportunity, we have invited 21 worldwide prominent speakers on these issues. Each of one will give a 35-minute conference, after which we will have 15 minutes for discussions, comments, and questions. But to begin with, we would like to carry out a tribute to Enrique's career, which will be in charge of four high academic authorities in different universities from Spain, France, and Chile. To begin, we will invite Professor María José Guibert, President of the Deusto University, Basque country, which has pre-recorded a video introducing the contribution of Enrique to Deusto University. So let us start watching this video.
It is a pleasure for me as rector of the University of Deusto to open this event entitled Workshop on Nonlinear Analysis and Control Theory in honor of Professor Enrique Zuazua on the occasion of his 60th birthday. Our good friend Enrique Zuazua began his collaboration with Deusto in the chair of computational mathematics in 2016, precisely because his area of expertise is closely linked to this field. His work in the interface between control systems theory and numerical analysis and scientific computing has led to some fruitful collaboration with different industrial sectors, such as the optimal shape design in aeronautics, and the management of electrical and water distribution networks. The main project that currently links him to Deusto Foundation is the DICON project. DICON project and ERC, European Research Council project, his second project of this kind. In this case, in the advanced category. It will last until 2022. Since 2016, the DICON project members have been working to make a breakthrough contribution in the broad area of control of partial differential equations and the numerical approximation methods by addressing key unsolved issues appearing systematically in real-life applications. To achieve this, they have been focused on three objectives. One, contributing with new key theoretical methods and results. Second, developing the corresponding numerical tools. And third, building up new computational software, the DICON computational platform, DICON blog, bridging the gap to applications. His scientific career in the field of research and applied mathematics has achieved great international renown and a major impact, both scientifically and socially. Last but not least, and particularly noteworthy, he has never lost his roots, his pride, and his Basque origins. Born in Eibar, Basque speaking and a member of a Basque Academy of Science Akiunde, he has managed to combine this local and global dimension in a very balanced way. Ohore handi bat da guretzat. We are very proud of him. Thanks to this collaborative networking, he has built relationships with international researchers and students, particularly with Latin American and international students, always available to participate in different meetings, to establish collaborations, and to welcome students and visitors. Throughout the life of DICON, this has been one of the cornerstones of the chair. In particular, its cooperation with the University of Chile, host of this event, is a good example of this. I wish you all a fruitful event full of sharing and learning. Eskerrik asko. Thanks. Thank you very much.
Thank you very much, Professor Guibert. And now we have Professor Amaya Mendikoetxea, President of the Autonomous University of Madrid, who will say some words.
Well, thank you very much, Professor Conca, for giving me the floor. I want to take this opportunity to thank the organizers of this workshop on nonlinear analysis and control theory in honor of Professor Enrique Zuazua for his 60th birthday, to give me the opportunity to welcome you all to this workshop. I cannot comment on the content of the workshop, but I'm sure it's going to be really interesting for all of you. I don't think Professor Zuazua needs much of an introduction, because you all know the prizes and awards he has received, the positions he has held at different universities and that he currently holds at different universities. We've already heard the rector of the University of Deusto. By the way, that's where I did my BA degree, because like Professor Zuazua, I'm a Basque in Madrid as well. So I'm proud to say that along with these other positions, Professor Enrique Zuazua is chair of applied mathematics in the Department of Mathematics in the Faculty of Science at Universidad Autónoma de Madrid. And he's involved in several projects at this university, European projects and national projects. And there are two aspects I'd like to mention, because my acquaintance with Enrique is quite short. It's just a few months ago. We met when I was running for rector at the university, but there are two aspects of his CV that I find particularly impressive, along with all the prizes and awards that he has received and all the honors that he has received and all the recognition that he's already got. One is the fact that he's supervised 24 doctoral theses, if the data on the webpage is correct. I think that's a lot of theses to supervise, and it just gives an idea that he's really concerned with the training of future researchers. And the other one is partly the one you're celebrating here, which is the collaboration, the intensive collaboration, international collaboration with departments and researchers all over the world. So Latin America particularly, but also many countries in Europe, the northern Mediterranean countries, in Africa, as well as Asia, such as China and Iran. I think a good example of that is the variety of speakers that you're going to have in this workshop from Italy, France, Romania, Germany, the USA, and Latin American countries such as Mexico, Brazil, and Chile. It seems to me that the speakers in this conference are not just colleagues, as we understand them, but also friends. And this is really remarkable because, well, you're all mathematicians. As far as I know, mathematicians do not work in labs, and they do not require like big groups to do research, unlike other areas of scientific endeavor. So what this tells us is something about Professor Zuazua as a researcher, but mostly as a person. So I'm very happy that he's receiving this tribute. I hope you have a very fruitful exchange in the next few days. And I really hope that Enrique also enjoys it. Thank you very much.
Many thanks, Amaya. And now it is the turn to address some few words to the Vice President of our university, University of Chile, Professor Alejandro Jofré, who in its turn, he's also an applied mathematician, an optimizer. So please, Alejandro, go ahead.
Thank you, Carlos. It's more than a pleasure to be here celebrating his Enrique 60 years. Hi, Enrique. I remember very well when he visited Chile many times, 3 or 4 times at least, remember. And it was very easy to know that Enrique was visiting us, because I was very active, moving, talking with different colleagues in many areas, not only mathematics, because sometimes we were discussing about the development of the country, economics, and about social science, and I know very well his interest also in this connection between mathematics and other areas like art, and it was we had very interesting discussion when he was pushing ahead his radio program on the Basque. I remember that many years ago, and always talking about, of course, PDEs and control and optimal shape problems and numerical analysis, but always thinking very deep on the connection between mathematics and some specific problem coming from the engineering, sometimes societal problems. So I was very impressed by his impact of different results that he had been developing in his career, And we see clearly about of a collection of prizes and awards in different countries, and not only Spain. And Enrique is a mathematician, which is very good to talk with him and to interact. And we see that the papers and contribution with many co-authors of different latitudes, and we were very happy to have Enrique in Chile so many times, and from him we met other colleagues around PDEs and Control, and I see here today some of them, and I say hello to good friends that are in this. There are more than almost 90 people connected now, and that is a good example that Enrique not only productivity but also this friendship with many colleagues from different countries. So congratulations, Enrique. The 60 years is a good age, and I know that you are very, very active, still very active, and we hope that you will continue to be active and to have you here in Chile soon.
Many thanks, Alejandro, for these very friendly words. We appreciate them. So to start concluding this first tribute to Enrique, we have the privilege to receive Professor Alain Haraux from the Université Pierre and Marie Curie, Sorbonne University. Alain was Enrique's PhD advisor at the middle of the 80s when we met Enrique for the first time, so more than 35 years ago. So if Alain, are you there? Okay, yes, I see you here. Okay, so please send some words to Enrique.
Okay, so Enrique, you see already 88. I hope it will overpass 100 participants. First of all, I would like to thank the organizers for this meeting, which promises to be very interesting, and to welcome all the colleagues who accepted the invitation to talk here. Age 60 is an important step in a career. I remember my own birthday party in Tunis 12 years ago. It gave a new impulse to my research to see all these friends from very different origins starting to interact, just because I changed my status from mature researcher to elderly man who deserves some consideration. I even remember that on this occasion, Felipe Alvarez, a very bright young Chilean mathematician, wished me another 60 years of mathematical research. He left us so much too early, and I want to recall here how important his achievements have been for several French mathematicians, including myself. What can I say about Enrique in 10 or 15 minutes that you do not know yet? You all know that Enrique started his career at Laboratoire Jacques-Louis Lyons. At that time, it was called Laboratoires d'Analyse Numérique de Paris 6 in Paris, by preparing a PhD degree under my supervision. He was introduced to me by María Esteban in 1985, and my first impression was that of a modest and somewhat shy young man. Then I understood rather quickly that, as intelligent people usually do, he always observed his interlocutor some time before revealing his true personality. In our first meeting, I asked Enrique a simple-looking open question which seemed logically solvable in finite time. The question was about the existence of zeros in a space-time cylinder 0t cross the domain for the solution of a clamped plate equation. Such results were previously known for abstract equations of the form u double prime plus a of u equals 0 when A is a positive self-adjoint operator with compact inverse on L2, assuming that the first eigenvalue of A is realized on some positive eigenfunction. For the case of B Laplacian with clamped boundary condition, it is known that such eigenfunctions can fail to be of one side. For instance, if the domain is an annulus. But of course, in such a case, all solutions with initial state made of multiples of that eigenfunction do change sign in any cylinder, so that it's hard to believe that the sign changes of the first eigenfunction really make the situation worse. When I asked the question to Enrique, he almost immediately asked whether it would be useful to find a positive supersolution for the eigenvalue problem. Then maybe the next day, he told me that a variational principle of Guido's Tampacchia that we recently learned from Brezi's seminar course should allow to do that. 1 week after, my question was solved. Finally, a few weeks later, we concluded that when the first eigenfunction is not of one sign, the global oscillation time becomes even smaller than the optimal oscillation time when the first eigenfunction has a constant sign, which is pi over square root of lambda 1, with lambda 1 the first eigenvalue of the bi-Laplacian. So the problem was entirely solved in an optimal way. A few months later, I started to ask him some rather technical questions directly connected with my personal main field of research, something that I almost never did with my students. The results were excellent and even helped my own research in the field. Chance sometimes plays a role, not only for our results, but to guide our careers. In 1986, Jacques-Louis Lyons, who was delivering his regular course at Collège de France, asked me whether I could help to write down the corresponding lecture notes. Unfortunately, or maybe fortunately, I had a long sojourn already planned in Tokyo, which made it impossible for me to follow most of his lectures in the fall of 1986. At that time, there was no Zoom facility. A few weeks ago, I discussed with Jesus Hernandez, who warned me that already as a high school student, Enrique had a reputation of exhausting all his math teachers, and told me that I should be very strong to control his incredible energy. And actually, I remember that during the years from 1985 to 1987, each morning, when arriving in the lab, after making 2 steps in the corridor, I saw at a distance Enrique saying, "As a matter of fact, it turns out that," or something of this type, referring to our previous conversation that I partly forgot, since I had the strange habit of sleeping at night. I decided to do something very unusual at that time. Now it's usual to have several advisors. At that time, you had one, and that was all. So on the pretext of the lecture notes, I decided to share the direction of research of Enrique Zuazua with Jacques-Louis Lyons. The plan worked perfectly. Although initially Lyons was a bit disturbed by the small southeast accent of Enrique, very soon he understood that Enrique never had enough work for his capabilities. The lecture notes were written, they were published, and as expectable, Enrique immediately got some sharp results in the field. To improve the plan, I did one more thing. I introduced Enrique to another talented young mathematician of Hungarian origin, namely Vilmos Komornik, who was following regularly and very actively Jacques Lyon's course, with whom he immediately started to collaborate on some fundamental open questions raised by Lyons, following a well-established tradition which attracted a large audience. Their joint achievements were quite remarkable and have been highly appreciated at the international level. One afternoon, after his recognition by Jacques-Louis Lyons, but probably before the defense of the PhD that was promising to approach the level of habilitation, I remember asking Enrique, near the metro station of Jussieu, whether he was planning to look for a position in France or go back to Spain. He immediately answered that his parents were getting old, and consequently, he preferred to go back to Spain to remain none too far from them. By chance, sometime later, I happened to talk with Yves Meyer, who just started to interact with Jacques Lyons on some aspects of control theory. Yves Meyer had a very strong influence on Spanish mathematicians, and with a 3-line firm recommendation letter from Lyons, Enrique obtained very quickly a full professor position in Madrid. The sequel of his career has been more complicated and less comfortable than the beginning, since he did not satisfy himself with doing such mainstream research. He wanted to fight to see his ideas produce concrete results. From the very beginning of the 90s, I stopped trying to control or even follow Enrique's activity, since I remembered the warning of Jesus Hernandez. From time to time, I had to review some of his papers, and very soon the situation was reversed, and my student had to review mine. As you know, it is the normal ambition of all fathers that their children become brighter than them. Fortunately, in my case, that goal was not difficult to achieve. I recently explained to Carlos Conca that partly because of the COVID pandemic, I realized part of my bucket list by starting to work on physics, not the physics of the mathematician, but the real one, having to do with the real world. Some of you might imagine that I wish to avoid competition with my British students, but it is not at all the point. How can a father even think of competing with his children? We are not really living in the same world as our children, and we should be aware of that reality every day if we really want any progress for our fragile human species. I wish you an excellent meeting and extend once more myself to all of you in this very special period where Enrique will start his next 60 years of research. Thank you.
Thank you very much, Alain, for such an interesting introduction to the initial stage of Enrique's career. Many thanks. His relationship with Laboratoire Jacques Lyons, with Professor Jacques Lyons, and with all the staff there. So now I think that Enrique, he would like to say something, or can we open him the microphone, please?
Yeah, I think I can talk now, right?
Yes.
So thank you, Carlos, Sebastian, Rodrigo, all the friends in Chile for taking the care of organizing this. It would have been great if we have had the opportunity to do that together, but I mean, it's great that we can do it in Zoom. This is fantastically organized, and well, so thank you for all that joined, and in particular to the 4 speakers we had that represent, you know, many things, of course, for me. So chronologically, I think Alain is first. I mean, he was my PhD advisor, and he represents probably this golden age of the Laboratoire Jacques Lyons, where there were so many people, right? Some of them were already very well established professors. So I had the privilege of attending the lectures person of Bresis that Alain mentioned, but also Ciarlet, Rabiar, Glovansky, Pironneau, Nedelec. I mean, that was, I still can, you know, I still live on what I learned in this first academic year in Paris, right? And then there was people like you also, Carlos, right? At that time, you were essentially like a postdoc. I mean, just a beginner, you know, a researcher in the CNRS, but that were playing this fundamental role of investing. I remember how many things you explained me in your office, in your Blackboard, about all kind of weak limits, homogenization, you know, functional analysis, compactness. I mean, these are things that are impossible to be understood if someone like you, in that case, you know, a consolidated expert was not telling you in person, right? And together with you, there were others that I remember talking very often, like Hervé Ledré or Thierry Casenave and many others. So I think then Alain and all this generation of, say, the French family of mathematics that, you know, provided me the opportunity to do all the rest. So for the others, yeah, I mean, later I have been a professor in Complutense, in Autónoma. I really thank Amaya, Mendikoetxea, the new rector of Autónoma that was here with us. I owe so much to Autónoma, right? So this is a fantastic campus, a fantastic university, full of opportunities. And I'm sure there are still many interesting things to be done in the mathematical sciences in the Autónoma campus. And then later to José María Guibert, the rector of Universidad de Deusto, that was kind enough to open his house so to, you know, collaborate with Autónoma on the development of the DICON ERC advanced grant. So I really thank, right? But then, you know, despite one is mainly working in one place or another, there are other places to whom one belongs, right? And in that sense, the Universidad de Chile, not only because very, you know, individuals like you or Jaime Ortega or Sebastian, Rodrigo are working there, but institutionally, I feel very attached in the sense that it has been a model, not only for me, but I think for the whole community of applied mathematics in Latin America is the Universidad de Chile. And I really thank that Alejandro also took the time to be with us. Yeah. So thank you all. I hope you will enjoy this workshop. Certainly the talks are extremely interesting. And well, I suppose that not all of us could be, you know, will be in conditions to be there all the time, but hopefully this will leave a trace, as Alain said, in order to continue in the near future with our collaboration. As you know, I am now a professor at Friedrich Alexander Universität in Erlangen, Nuremberg, the university where Felix Klein, you know, was working in the turn of the 20th century. It was Felix Klein who already indicated, right, that you know, mathematics should be driven by schools, not only by individuals, and therefore that, you know, education and research should come together. I think Gunther Leugering is among the speakers. I owe Gunther also, as I do to many others in this audience, really a lot. He gave the generous opportunity for me and my family to join FAU, that is much more than a university, right? It's a universe of opportunities, and you know, together with the Humboldt Foundation, the conditions are so good. I mean, that it was simply impossible to, you know, not to accept the offer of joining there. And so the new home, our new home, is there in Erlangen, and you are all welcome to come anytime. I hope that we will be able to develop there the activity that we have developed, you know, in Madrid, in Bilbao, in Basque, in Chile, in many other places. Well, now you have a new home for all of you, and this is in Erlangen. Thank you. Thank you again. Gracias, Carlos.
Thank you to you, Enrique. So we still have some 15 minutes before starting our real meeting. And if someone of you among the people participants would like to say something about, for example, this period in Paris 6 during the last 2 decades of the last century, which were real golden years for all of us, maybe you can do it. Huh? So the microphones can be opened to all of those who want to say something now. I see here Eve Mayer.
Hola.
Hi, Eve. How are you?
Fine. Estoy bien. Estoy perfecto.
Thank you very much for speaking Spanish.
No, but tendré que hablar en inglés por mi charla. No la daré en castellano.
Okay. So in case nobody wants to add something, we can start with our, okay, Gunther. Gunther,
Well,
you want to say something?
Yes,
Okay.
I want to say something because I realized that unfortunately our university leadership wasn't able to come today because Wednesday is the day for all the meetings. So I take the opportunity, you know, as retired vice president for research to say a few words. So at FAU, we are extremely proud to have received Enrique in 2019 for the prestigious Humboldt professorship, which is the highest award in Germany that you can possibly have. Also, previously, we had him as a Humboldt awardee, so the Humboldt Science Award is also a prestigious award. And before that, even in 2015, just when I became vice president for internationalization at that time, he became FAU ambassador. And so he is taking the logo and the contents, as he mentioned this in a few sentences, into the world, and we are extremely proud to have him. And I personally, I know him also since '87. I think Enrique, we met in this fantastic and legendary conference that Alfredo Bermudez at that time organized in Santiago de Compostela. And it was an orgy, right? I mean, the dinner we all remember well, I think, and also it was, of course, scientifically a great, very great impact that we both, I think, experienced there. So thank you, Carlos, for taking this fantastic opportunity to receive Enrique for his 60th birthday. We did a little bit at FAU, but not in this, of course, in this framework. And thank you to all of you to attain this.
Thanks to you, Gunther. So we have two people here that have raised their hands. First, Jaime Ortega.
Yes, hello, Carlos. Thanks for your hard work. It's great to be here. I want to say only thanks, Enrique, for this years of friendship, for this year of mathematics together. I'm one of the most old students from the group of estimados. I'm one of the estimados group, the old student of PhD in Complutense. And I have only good remembers of this time in Madrid and in Bilbao, in several places. And I hope to see you soon personally. And this will be a very beautiful party for all. And thanks for being part of this party only. And regards, Enrique. You are a good friend. Thanks.
Thanks to
Gracias,
you, Jaime.
Jaime. Gracias.
We also have here Rajesh Mahavedan, who would like to say something to Enrique.
First of all, I hope you hear me. You?
Yes, perfectly.
Yeah. First of all, very happy birthday to Enrique's happy 60th and many more happy years to come, and active research especially, and good times with your family. So there were many happy moments I passed in the company of Enrique, especially in the conferences which Enrique organized in Basque. It was a moment to meet people and exchange ideas. And so actually, it's these conferences also some sense reflect Enrique's personality, because I mean, he's a powerhouse of like energy and meaning ideas. And so these kind of contagious and spreads to other people. And I wish I had energy like him. I mean, so it's the only aspiration I can have. And so again, so also, I mean, I enjoyed very much the football matches I played with him. And so, okay, so all the best.
Many thanks, Rajat.
Yeah.
So I see also that Marie has raised his hand. So
yes, yeah, thank you very much. I want to say a few words about, if you know everyone in the world, you have two homes. Enrique, the first home is Spain, and his second home is Puerto Rico, where his wife is from Puerto Rico. I get the opportunity to meet Enrique in Puerto Rico, and since then, we've become very good friends, good collaborators. And before that, I did my PhD in semi-group theory, and while evolution equation, I didn't know anything about control theory. And since 10 years, every year Enrique came to Puerto Rico, Enrique said, okay, he introduced me to control theory. And the last 10 years, all my papers are based on control theory. And only because of Enrique. I'm really thankful also you, Carlos Conca, and that knows that even if I may be the last one who knows Enrique, we are now best friends and best collaborator. And every year, since 7, 8 years, every year I meet Enrique, he travels to Puerto Rico or I go to Spain. We are really good. And thanks Enrique for putting me in control theory. That helped me a lot to survive in the United States. Thanks, Enrique.
Thanks to you, Maria. Very emotional words. So I think that we can now start with our conferences. And the first speaker, we have the privilege to receive Professor Jean-Michel Coron, University of Pierre Marie Curie. Jean-Michel was a former student of Jaime Ortega. At the beginning of his career, he started doing research in nonlinear functional analysis, but sometime after that, he started working on control theory, where he is today one of the most prominent experts in the world. And the title of his talk, his conference, will be Obstruction to a Small-Time Local Controllability on a Kdb Control System. So, Jean-Michel, please go ahead.
Thanks, Carlos, for the introduction. First, I want to say that it's a great pleasure and great honor for me to have been invited to give this talk in honor of Enrique. Enrique has made numerous pioneer contributions, which has strongly influenced the works of many people, and in particular me, as we are going to see. In fact, it's already thanks to him that I moved to control theory. I listened to some of his talks, and I was very impressed by the subject. So, as mentioned by Carlos, the subject of this talk is about obstruction to small-time local controllability of a Kdb control system. So the outline is here. First, I will present our results. It's a joint work with Armand Koenig and Jaime Ortega. And then I will present some prior obstruction to small-time local controllability. And finally, I will give some insight about the proof of the obstruction to small-time local controllability. So let us start with the statement of the obstruction. So the starting point is a pioneer work by Enrique Fernandez-Cara, Enrique Zuazua about the null controllability of some semi-linear equation, very general, in fact, semi-linearity equation. In this paper, the two Enrique considers it equation, semi-linearity equation given by 1 with the usual notation, and you have a part of the domain which is called small omega, on which you have the control. And about the non-linearity f of y, they assume that they have this decay rate at infinity. And there are remarkable points in these works. They prove the global, so global null controllability in small time. Global, which means that the result is for any initial data. So this is remarkable. And the other point is that you get the null controllability in arbitrary time. So this is also very impressive. And finally, I want to mention that with the type of nonlinearity which are considered in this very important paper, you may have blow up in finite time if you don't have any control. That is, if you take q equals 0, there are many initial data for some f satisfying 2, such that you have blow up in finite time. So this is a pioneer work for which you can avoid the blow up thanks to the control. And this is really a masterpiece. So maybe I will give some insight on the proof, which has been very influential. For simplicity, let us assume that f of 0 is equal to 0 and define g of y is equal to f of y divided by y. So you start from some initial data which is given, y0, and you want to construct a control such that you can move to 0 at time capital T. And they construct the control by showing the existence of a fixed point to the map y gives z, where z is a solution of the linear equation 3, where g of y is a potential, and the control is u. So it is known that this linear PDE is controllable in arbitrary small time. So you fix the time, and there is a u such that if you start at y0 for z, then you arrive at time capital T at 0. And they choose for u the best u, that is the u which is minimizing the L2 cost, for example. It's not mandatory. You can find some other property. And in order to prove the existence of a fixed point, they give a very important estimate on the cost of the null controllability of the linear equation 3, where you have this potential g of y, which depends on x and time. So this is really a very important work. So, of course, it's difficult to compete with this this remarkable result. So we move in some other direction. Instead of positive result, we look for obstruction to controllability. We are also dealing only with a local result. And we are interested in the case where the linearized system is not controllable. And also in the case where the nonlinear term is going to give some new phenomena. So we start with the control system that we want to study. It's a system which has been introduced by Lionel Rosé in 1997. This is a Kdb control system. So you have the equation for the first one is the Kdb equation, yt plus yx plus y triple x plus yx is equal to 0. X is between 0 and L, and the time is between 0 and t. We have the boundary conditions, so you must have 3 boundary conditions. The first 2 are the Dirichlet boundary condition. And then for the last condition, you have the control. Yx of TL is equal to u of t. U of t is a control, and the state is the function y at time t, which belongs to L2 of 0L. And you want to study the controllability of this equation. So we start with a local result, and then the idea is to linearize the system. This is what it was doing Lionel in 1997. he considers a linearized equation. So you forget the term y(x), and you get the equation 5. And he proves that this equation is controllable, this linear equation is controllable for any t, if and only if L is not critical, in the sense that L does not belong to the set N, which is defined in 6. And moreover, he proves that in the case where the linear system is not controllable, the part that you cannot control with a linear system is a linear space, of course, but that we are going to call M. But this linear space is of finite dimension. So this is very interesting result. And from that, he succeeds to get the small time local controllability, that is the local controllability for any time t. What does that mean? It means that you have this 0, and the local controllability means that for any ball of reduced epsilon, this is for the state space. Of course, the norm is very important. There is another ball, a smaller one, such that if you have 2 states in the smaller ball, the blue one, then you can move from the first state y0 to the second state by using a control which is less than epsilon for some suitable norm. So this is a problem of local controllability in time t. And Lionel Rosier, using his result on the linearized system, gets by some inverse mapping theorem that the Kdb control system is locally controllable for any positive time. So this is a small time local controllability. Everything is small. The time, the state, and the control are small for suitable norms. And the notion of smallness depends a lot on the order. So what happened now if the length is critical? So I proved with Emmanuel Crépeau in 2004 that if the dimension of M is equal to 1, M is the linear space which is not controllable by the linearized control system, then our system is again small time locally controllable. And there are cases where the dimension is equal to 1, for example, L equal to pi. So it remains open the case where the dimension is larger than 1, and that was done by Eduardo Serpa and Emmanuel Crépeau later on. They prove that if the time is large enough, then you have the local controllability of the nonlinear control system, thanks to the nonlinear term. The linear system is not controllable, but the nonlinear terms give you the controllability. And the proof relies on some power expansion. So you look to the order 1, you get the linearized control system. Then you have the order 2, you do some expansion, you have the order 2, the order 3, and so on. And roughly speaking, the idea is that, for example, if for the order 2, you have the controllability, then the nonlinear system is indeed locally controllable. And the fact that this is for the dimension M is equal to 1, you have to go to the order 3. This is the order 3 which gives something, the order 2 gives nothing. This is from this is because the order is odd that you can get the small time local controllability. When the order is 2, it was not clear if it is small time locally controllable. We know it's locally controllable if the time is large enough. But what about small time local controllability? This is the question. If you assume that the dimension of M is larger than 1, is it true that for every positive time, the control system, the nonlinear control system, is locally controllable in time t? And we give a negative answer recently with Armand Koenig and Wyman and Nguyen under some extra assumption. We assume that the length is critical, so it's given by 8. But you have some other assumption. You assume that 2k plus L is not a multiple of 3. So it implies that the dimension is larger than, dimension of M is larger than 1, but it's not equivalent. It's a more restrictive assumption. Then we prove that this then the control system is not small time locally controllable for some norms for the control and the data. For the control, this is the H1 norm, and for the data, the initial datum, this is H3 norm. That is, you cannot move if you have, even if a state is very small, you cannot move if the time is too small, you cannot move to 0, for example. It's not null controllable in small time. So some problems are still open. You see, we have some stronger norm. in our result. So for example, the control is in H1, and in the result by Lionel, the control is only in L2, and the state also is in H3, while for the Lionel result, the state is in L2. So what happened for this natural space, that is the state is in L2 and the control is in L2, we do not know. There is also the problem of our assumption, 2 times k plus n is not a multiple of 3. This is a stronger assumption that the dimension of m is larger than 1. So the natural question is the condition dimension of m larger than 1, is it a sufficient condition to get an obstruction to the small time local controllability? And the next open problem, we know that for some value of k and l, the control system is not controllable in small time. What is the minimal time for local controllability? This is the last open problem that I would like to mention. Some other example. This is the water tank control system. It's a system which has been introduced by Dubois, Petit, and Rouchon in 1999. The modelization is through the Saint-Venant equation, and you assume that the control is the force that you apply to the water tank. So there is a natural question which is here. You start the water tank, it has some position. The level of the water is horizontal. The speed, every speed is equal to 0. The speed of the water and the speed of the tank are 0. And you want to arrive, this is the initial state, and the target, the situation where you want to arrive, it's almost the same, except that the water tank has moved a little bit. Is it possible to make this motion? For the linearized control system, it will prove by Dubois, Petit, and Rouchon that if the time t is larger than square root of L times HE, G is the gravity constant, L is the length of the tank, and HE is the height of the water at the equilibrium. This condition is sufficient to imply that you can do the previous motion, steady state motion, for any time which satisfies this property 10. So you may ask for the linear system. You may ask, is it working also for the non-linear system? And the answer is no, as we proved recently with Armand Koenig, Wymin, and Guyel. We need more time to do this motion. So this is an example where you have a motion that you can do for the linear system, but you cannot do it for the non-linear system, at least if the time is too small. You can make it for large time. That was what I proved in 2002. But you see a difference between the linear situation, where you can do some motion in some fixed time, and you cannot do the same motion in the same amount of time for the non-linear system. So there was some prior obstruction to small time local controllability for partial differential equations that I would like to present now. The first one is again suggested by Pierre Rouchon. This is a quantum particle which is in a moving box. So you have the wave function psi. It satisfies the Schrödinger equation. And this is the state. Now the state space is not L2, but you have to, it's a sphere. The norm of psi in L2 is equal to 1. So we are working on a sphere. And an equilibrium is the first eigenvalue. It's not exactly equilibrium because you have to multiply if the eigenvalue is lambda 1. The trajectory is phi 1 exponential minus I lambda 1t. And the natural question for local null controllability, we start with something which is close to this function. Is it possible to move to this phi 1 exactly? And there is the same problem as for the water tank. You start with a box which is at some place, and the initial data is phi 1, and you want to arrive to exponential minus I lambda 1t, phi 1, but with a box which has moved a little bit. And again, for the linearized, and there is also some global result. You can move for the first eigenvalue to the second one, for example. And what is interesting is again that the small time local controllability, the small time steady state motion is possible for the case of the linear system, but it's not possible for the nonlinear system. We need more time to do that. There are also some results about global and local controllability in large time, in particular by Karim Bochard and Nersessian. but I want to present you the obstruction to small time local controllability around phi 1. So I introduce some notation. X is between -1 and 1. D is the position of the box. Psi is a wave function. And you assume that the control is small, because we are studying small time locally controllable, which means that everything is small. The time is small, the control is small, and the state is close to phi 1 exponential I lambda 1t, which is psi 1. And then you have the control system, which is given by the equation 12. The u of t is the control. And you have the position of the box, which is given by d. The speed of the box is s. And so we have this equation. There is a part which is a PD equation, but there is a part which is ordinary differential equations. They are coupled. And you want to prove that you have some obstruction to small time local controllability. So we define theta in 17, which is here. And then you define this V of t. So we do some computation. And the point is that V of t, you can show it's given also by 18, where V0 of tau is given later on. And then there is a sign. That is, if you look to, you see you have S of t, V0 of tau, but V0 of tau is like S of tau. So you have something like, which is like S of tau square, which means that you have a sign for V. And in fact, you can prove that if the time is too small, the real part of V has to be positive. And in fact, it is strictly positive if you move a little bit. If you move a little bit, the V is going to be strictly positive, which prevents you to get the local controllability. You have a sign. Something is moving in the bad direction. So it is something which is very classical for control system in finite dimension. In order to prove that the system is not controllable, you prove that you can move in some direction, but not in the opposite. You are living in a half space. So there is also some nice result due to Frédéric Marbach in 2018 for a control system introduced by Sergio Guerrero. It's a Burger's control system, and the control is U of t, which does not depend on x. And Frédéric Marbach proved in 2018 that this system is not small time locally controllable. There is an interesting problem: is it large time locally controllable? We really don't know for the moment. And the proof by Marbach relies on very interesting tools, scaling, power series expansion as the positive result for local controllability of the Kdb equation, and new quadratic estimate which give you that, again, there is some quantity such that if you move, it's going to be positive. And the fact that it is positive implies that it's not small time locally controllable. It's not locally controllable. There are some other examples, the Schrödinger equation with bilinear control by Karim Bochard and Olga Morancé, and some nonlinear parabolic equation by Karim Bochard and Frédéric Marbach. And in all of these results, in order to prove that you do not have small time local controllability, you prove that if the time is too small, then the state is going to be in a half space. Of course, you have, so that is something is going to be positive. So of course, the difficulty is to find these things. This is a general strategy, but to do it for a specific situation can be very complicated. Of course, when you give a talk, you have to explain why your result is more difficult to get than the previous one. So this is a slide on this. The first point is that we are dealing with boundary controls. And boundary control usually is more complicated for the obstruction to small time local controllability, because, for example, in finite dimension, there are many results which gives you some obstruction to small time local controllability, which relies on iterated Lie bracket. But we know that iterated Lie bracket, when you have boundary control, it's difficult to understand what it is. And when you understand what it is, in fact, you can prove usually that they are not in the state space. The direction given by the Lie bracket are not in the state space. There are some distributions that are not in L2, for example, in the case we are considering. And also, you cannot perform the change of time scale introduced by Frédéric Marbach, because this change of time scale is going to introduce a boundary layer. And the boundary layers in the case of the burgers control system can be handled by using the maximum principle. But in the case of the KDB equations, there is no maximum principle, so you cannot use this method. Moreover, it's better to not use this method if you can make it, because usually it gives some better estimate about the obstruction of about the time for the obstruction of small time local controllability. And the next point is that if you look to the linear system, forget the control, then the operator is neither self-adjoint nor adjoint, and the eigenvalue are complicated, and also the eigenfunctions. So what are the main steps of the proof to small time local controllability of our result? I would like to present the idea on a very simple example. You consider a system in finite dimension. So this is system 22. We have the state y1, y2, y3 is in R3, and the control is a scalar control. It's U. And the dynamics is given by y1 dot is equal to U, y2 dot is equal to y3, y3 dot is equal to minus y2 plus 2 times y1 U. So the state is of dimension 3, the control is of dimension 1. You want to study the local controllability of this system. So when you want to study the local controllability, you start with a linearization. It's like when you have a map from RP to RP, you want to see if it is locally surjective, you just linearize. So we do the same. We linearize and we get y1 dot is equal to U, y2 dot is equal to y3. And concerning y3 dot, the term, the quadratic term just disappears. So you get y3 dot is equal to minus y2. So this control system, the linearized control system, is clearly not controllable. It's not controllable because the control has no effect on the dynamics of y2 and y3. For example, if y2 and y3 at the beginning are not 0, they will not be equal to 0 for all time, in fact, whatever we do with the control U. You can prove that this system, the nonlinear system 22, and I will go back later on about the time, is controllable in large time. But what about small time local controllability? For this system, the answer is easy to get because you can use Duhamel's formula and you can more or less explicitly compute the solution. So you get 24, y2 of t is equal to the integral from 0 to capital T, cosine capital T minus t, y1 square dt. And you can get also equation 25. So, and the first equation gives you that y2 dot, y2 of capital T is larger than 0, is non-negative if the time, if you go back to the expression, if the time is between 0 and pi divided by 2. And the other equation about y3 gives you that if y1 of t is equal to 0, then y3 of capital T is less or equal than 0 if the time is between 0 and pi. You see, if you go back to 25, you easily get that. So you see that the system is not small time locally controllable. And in fact, equation 26 shows you that you cannot locally control the system if the time is between 0 and pi divided by 2. And 27 gives you that you cannot control the system if the time is between 0 and pi, even locally. And also, in fact, you may wonder what happens if you have perturbation of this control system. So let me go back to the system. You see, y1 and u, they have the same size. y2 and y3 have the same size, but y2, which is also like y3, it's a quadratic term because it looks like y1 u, and u is like y1. So in some sense, if you do a perturbation of the first equation, y1 dot is equal to u plus y1 square. y1 square is smaller, much smaller than u, okay? So it's going to work again. For the second equation, for example, y2 dot equal to y3, you do the perturbation by y2 dot is equal to y3 plus, let's say, y1 to the cube. It's again a perturbation compared to y3. And you can get also the fact that it's not small time locally controllable. And this, and so on. So this, you can do that by showing the following inequality. For example, the one which is the most interesting one, 29. For any capital T between 0 and pi, there exists delta such that y1 of t is equal to 0, implies that y3 of t not only is less or equal than 0, but you have some estimate in terms of u. And this is really what we are going to do for the Kdb equation. We are going to try to get some estimate like 29. So the first step for 29 is to understand what are the controls which allows you for the linearized system to go from 0 to 0. Of course, I should have also mentioned that for this toy model, which is a finite dimensional control system, there are tools in finite dimension which allows you to prove very simply that this system is not small time locally controllable just by computing iterated bracket. There is a necessary condition due to Sussman for small time local controllability, which relies on iterated bracket. You can check that this condition, this necessary condition, is not satisfied. And there is some more general obstruction which has been obtained recently by Karin Bochard and Frédéric Marbach, which are very interesting. But again, iterated bracket, we do not know how to make it work for boundary control, for PDE. So we are looking for something different. So we are looking for the Kdb equation to the analogous of 29. So the first step is to understand what are the controls which allows you to move from the linearized system from 0 to 0. And then to do some power series expansion. So let me explain the power series expansion first, maybe. So we have, you expand u in terms of some parameter epsilon. So u is epsilon u1 plus epsilon square u2, and you do the same for y. So for example, yx is epsilon square y1, y1x, and so on. So if you do the expansion to the order 2, you get two coupled systems, 33 and 34. And roughly speaking, if you can prove that this coupled system is controllable, then you can expect to prove that the nonlinear system, the true nonlinear system, the starting one, the Kdb equation with only one control, is in fact small time locally controllable. And that was what was used by Eduardo Serpa, Emmanuel Crépeau, and myself. But the argument was by contradiction. To prove the controllability of 33 and 34, it was more an argument by contradiction. You try to find control such that y1 is going from 0 to 0 and y2 is moving in the direction, in some direction of m. But for that, we use some argument by contradiction. And in our work with Armand Koenig and Wilhelmine Nguyen, we use another method. We try to really understand in which direction we can move. So we first characterize all the controls U1, such that for the linearized control system, you go from 0 to 0 at time capital T. And this is done by applying the Palais-Wiener's theorem and the Fourier transform with respect to time of the solution Y1. And this is the statement that I'm going to present. So we define Q and P, where the lambda I are the roots of the polynomial given in 35. And with this, you have the result. That is, L is fixed, doesn't need to be critical. T is fixed, and you are looking for U in L2 of minus infinity plus infinity, with support included in 0T, which steers the linearized constant system from 0 at time 0 to 0 at time capital T. And the necessary and sufficient condition is given by this Palais-Wiener condition. Yes, 38 and 39. That is, if you have a U dot, if U is such that you can go from 0 to 0, for example, you have, this is the part that we are doing, you have 38 and 39. Now, of course, this is not the end of the story because we want to have this coercivity. We want to have this sign for some quantity. And this is a difficult part, in fact. So we assume that we introduce some notation. We assume that the length is given by 40. So the length is critical. You define eta1, eta2, and eta3, P and capital E is a complex number, you define this function phi of x, this function psi of t and x. This function psi of t and x is real. And the key points are here. First, E is not equal to 0 if and only if 2 times k plus L is not a multiple of 3. This is a place where our assumption 2k plus L is not a multiple of 3 is appearing. In particular, if 2 times k plus L is not a multiple of 3, you can prove that psi of 0, psi at time 0, is not 0. Then you can show that psi is a solution of the linearized Kdb equation. And it satisfies this strange boundary conditions. That is, there are now 4 boundary conditions, which is a little strange. Psi t0 is equal to psi tl is equal to psi xt0 is equal to psi xtl. So we have 4 boundary conditions instead of 3. But this is the fact that we have these 4 boundary conditions, which tells you that the linearized control system cannot be controllable, because if you have a solution to the linearized control system, if you multiply this solution by psi, integrate from 0 to L, you have a quantity which does not depend on time. And now we are going to see what happened for the order 2. And the estimate that I presented before, the coercivity, is just given by 50. You have this quantity, the left-hand side is more than C times the norm of U, h minus 2/3 to the square. And this is the main step of the proof. Because this quantity, you can see it's a linear quantity with respect to y2. If you do the expansion, we go back to the expansion, you have this equation, the linearized system, which is 33, the expansion to the order 2, which is 44. And then you translate the equation, the inequalities I presented before. This is just 55. But 55, the left-hand side of 55 is a linear expression in terms of y2. The left-hand side of 55 is just the left-hand side of 57. So this is now you get the obstruction to small time local controllability for the order 2. But we have also some inequality, and this is very important to have the inequality. So obstruction to the small time local controllability of the order 2, just you take you want to have y2 t star is equal to 0. So the first term is 0. And then you have a condition which must be satisfied. You have a sign. You have a sign for the initial data. And you see this is linear with respect to y2. And you use the fact that psi 0 of x is not identically equal to 0 to get the obstruction to small time local controllability of the order 2. But the fact that you have some inequality, not only because if you have, for example, for 57, if you have only that the quantity is more or equal than 0, you cannot conclude. You cannot conclude because the order 3 will give something. The order 3 will give something. But the fact that it's larger than C times the norm of U square, h minus 2 divided by 3, prevents you to get the small time local controllability thanks to the order 3. You will get an obstruction to small time local controllability thanks to this inequality 57. And of course, this is not an easy task, but you can do some computation. And this is a place where we need to have some more regularity about the control, in fact. So you get the obstruction to small time local controllability for the Kdb equation when 2 times k plus L is not a multiple of 3 for critical length. So in order to conclude, happy birthday, Enrique. And I'm going to stop here. And thank you very much for your attention.
Okay, thank you very much, Jean-Michel, for such a nice talk. So now microphones and the written chat is open for discussion, comments, and of course, questions.
Carlos, can I comment something?
Okay.
Well, Jean-Michel, hi, Enrique.
Eduardo.
Well, I'm very happy to see this result, Jean-Michel. It's very impressive. And more than a question, I have a comment. especially directed to young researchers here in the audience, because I remember that we were working on this. We were looking for this result in 2008 with Emmanuel Crepeau under your direction, trying to build these trajectories to get in this space M. It was a happy ending for us because it was very, very hard. But at that time, I remember that with that contraction that we made of particular solutions, we knew that if we were able to arrive to a good direction in the space M, we can do the whole space, and we always arrive to the bad one. So it was so it's in this kind of conference and life for the researchers, you always see the stories with happy ending. And this is one for you and Armand and Jaime, but it took 12 years. So that's an important signal for all, especially young researchers. So I would like to emphasize that.
Thank you very much, Eduardo. So maybe I could comment a little bit. You see, Eduardo with Emmanuel Crepeau, for example, let's assume that the dimension of M is equal to 2. You can prove by arguing by contradictions that it's possible to enter in M. And then Eduardo Serpa and Emmanuel Crepeau, they just wait a little bit. And then this direction, it moves around the origin. So you can cover all the space. But in order to have this rotation, you need some time. This is why there is some time for small time local controllability. But for example, for the conjecture about what is the best time, maybe the time which is given in general, that is for the case NEK and NEL by Edouard Serpa and Emmanuel Crepeau, maybe it's too long, but it's quite possible that the one that was obtained by Eduardo in the first paper, when the dimension of M is equal to 2, it's reasonable to expect that maybe the time that was obtained for the local controllability by Eduardo, maybe it's the best time, quite possible.
Okay. Is there any other question, comment?
May I ask a question?
Or Professor Chang?
Not Professor, but hello, Jean-Michel. Thank you for your fantastic talk. This is the result that I really appreciate, and I would hope that I would have the chance to get. Certainly I didn't. So, okay, the question is like, you proved the small time local controllability, and this is a very incredible, but do you have some idea about, can we prove some small time local controllability by use very large control term? So which means,
yeah, that is very, of course, this is very interesting because it's quite possible. You see, in the definition that I gave for small time local controllability, everything is small with a different scale, in fact, but the time is small, the control is small, and the state is small. It does not prevent the problem which is raised by Sheng-Yuan, which is the case where, in fact, maybe you still remain, the state still remain in a small ball, but the control maybe is large. And this is a very interesting problem. Yes, for sure, it's very interesting. I don't know what is the answer, but if we go back to my result, our result, we prove that there exists time t0, there exists some delta, such that but there is this problem of the control which is less than delta. If we do not assume that there is this problem on the size of the control, it's open for the KDB. For some Schrödinger equation with August Tasman and Carrie Bochard, I get some obstruction to small time controllability for any control, but that was very special for KDB. And also I think that it's not exactly your question because the state is not small, but there is no constraint on the control. And we prove that we do not have the global null controllability, the analogous of the global null controllability in small time. even if it is true for a large time. And in this case, there is no constraint, there is no bound on the control in the statement. But this is very special, and for the Kdb equation, I don't know what is the answer.
Okay, thank you a lot. It's very nice.
Okay, if there is any other question, you can raise your hands.
Can I ask something?
Yes, of course. Enrique, please go.
Merci, Jean-Michel. Merci, Carlos. So Jean-Michel, in those cases where there is a minimal time, then is the system controllable at the minimal time, or so the condition is, or not?
No, probably not. I say minimal time, but it's infimum, in fact. If for example, if you look to the toy model, the minimal time is pi, but pi is not working. You have to take pi plus delta.
Okay. So pi might not be working.
Yeah.
And are there examples where at the critical time it might work, or?
In finite dimension, I don't know.
Okay.
Probably not. Probably I would say not, because if you can make it maybe for the, I think this is more or less open. That is, if you move a little bit, and it's going to remain. It's not. Of course, I should have mentioned, of course, that the problem of the time for PDE is already important for a linear system, but in the case of finite speed of propagation, here we are looking, for example, where the finite speed of propagation is infinite. But you are right, for example, for just the transport equation, if you look to the null controllability for yx plus yt plus yx at some interval, and you put u of t is the control, you're right, at the time capital T equal L, it's controllable. But I would say for the nonlinear system, the situation might be different. The examples that I know, it's not working for the limiting time.
Okay, so yeah, I mean, I was thinking on, you see these problems we looked with Emmanuel and Loeak. It was a heat equation with non-negative controls. Then when you push the time to be minimum, you get Dirac delta controls, right? So I mean, you achieve the controllability in the minimal time, but at the price of making the control more singular. I mean, it's unbounded.
Yes, you're right. I think if you allow Dirac masses, maybe you're working at the time capital T equal to pi. Yeah.
This could happen. Yeah. Okay. Thank you. Anyhow, very interesting talk indeed. Very much. So yeah, I mean, so what Eduardo said is that it took 12 years to prove this result, right? So this is very encouraging. This is very encouraging for young people, right? So that, I mean, they can never give up before the first 12 years, right? Yeah.
Thank you.
Okay, many thanks, Jean-Michel. So we can congratulate you once again. So thank you very much.
Thank you for the invitation.
Okay, so it's a great pleasure for me to introduce our second speaker today. He is Grégoire Alain, professor at the École Polytechnique of Paris, but he has a very similar position at the Université Pierre and Marie Curie. At the beginning of his career, he was a specialist in homogenization, multi-scaled analysis. He was at the base of one of the most celebrated methods in periodic homogenization, the two-scale convergence method. And today he's also a specialist in shape and optimal structure optimization. And the title of his talk conference will be Shape Optimization with Imperfect Interfaces. So, Greg, you can go ahead.
Okay, thank you very much for the introduction, and Thank you also for inviting me. It's a great pleasure. Can you see my slides? Good, excellent. And I hope you can hear me well. So it's a great pleasure to participate to this birthday of Enrique, a long friend. So indeed, I'm going to talk about a topic in shape and topology optimization. And I choose this topic because I did it with a Chilean postdoc, Matías Godoy, that some of you know, and also together with my colleague, assistant professor here at Polytechnique, Benjamin Bogosel. So the content of my talk is following. I will first discuss the motivation of this work, which has something to do with so-called additive manufacturing, and more precisely the question of supports in additive manufacturing. Then I will first discuss the case of a two-phase design, optimal design problem in thermal conduction, because things are a little bit simpler. And then I will go in a third section to the case of the elasticity, linearized elasticity system for supports. And then I will finish with some conclusion. Let me add that this work has been funded by a project which is called the SOFIA project, which is a project funded by the French government, which has many partners, so the CNRS for the academic side, but then some companies like Adobe, Michelin, Safran, and some other ones. Good. So what is additive manufacturing? You all heard probably about this. This is a way of building structure layer by layer. Here I'm talking mostly about metallic additive manufacturing. And one of the main interests of this new way of building a structure is that you can have very complicated shape and topology. So here, I don't know if you see my mouse. I don't know if the mouse can be seen. Anyway, at the bottom of the slide, you can see two structures with very complicated topologies that have been built by additive manufacturing, and that will be very hard to build with other techniques like molding or milling. Okay, so here is a principle of powder bed metallic additive manufacturing. Typically, you have a build platform. On this build platform, at every layer, there is a roller that put one layer of metallic powder, and then you have a laser beam that travel above this layer of metallic powder, and that will melt this powder where you want to build something, and will not melt the rest of the powder. And once you have melted one layer, you put another layer of powder, and so on and so forth. So it is a process that takes some time, but in the end, so you see here a picture where the dark gray is the metallic powder which has been already melted. You clearly see the spot of the laser beam, and the light gray is still the powder. And at the end of the process, you just remove the powder and you have your structure which pops up. Okay, good. So also, it is very convenient, and many industries are interested in using it. There are still some constraints. In particular, if you want to build, for example, an horizontal beam, this horizontal beam will be carried by powder, and powder is, is very fragile. So the beam will be probably a little bit bended when you melt it. So it's very hard to build a structure which have so-called enverang surfaces, so which have surfaces which are almost horizontal, because they will, kind of dig into the powder when you melt it. Then, of course, when you melt it, you bring a lot of heat, and then in the melted part, what remains after the passage of the laser beam is some thermal residual stresses, and so the structure will be deformed by cooling down, because you have some thermal residual stresses that stay inside. In particular, you can have an upper bending of the structure that will probably stop the roller that put a new layer of powder if it has bent too much. Okay, so to accommodate those constraints, there is a trick of using so-called supports, and the role of the support is to support inclined surfaces, horizontal surfaces, if you want, and then also to fix the shape that you want to build to the base plate at the bottom layer, which is fixed at the machine, and so the support can fix the structure, and so it will not deform too much under the effect of thermal residual stresses. So here you have a picture of one structure, and you see below the structure, which is inclined, you see supports which are built in metal, I mean with the same metal, and the role of those supports is just to support the structure. At the end, when you have built your structure with the supports, you remove the supports. So of course, because you remove the supports, this is some metallic powder which is lost. So you want to have some support, but the minimal amount of it, because building takes some time and costs some money. So you want to use support if necessary, but in a minimal amount. So here are two examples of support. Here, this is a picture of my PhD student, Martin Beer, who is doing his PhD at Safran. And so he has built a small, this is a very small sample, something like 5 centimeters long, MBB beam. And you can see on the right, supports which are not very well designed, by the way. And actually the supports, the goal of this picture is to show you that these supports are very thin, and they are in some sense pre-cut. You have some kind of a collection of holes close to the connection with the structure, so that it will be easy to remove. Okay. Another example of supports is here. That's a picture that I've taken on the webpage of Magix. Magix is a software that allows you to design supports, and you see that the support have a kind of a tree or branching structure when they connect to the structure. You see, because you want to remove them, so you want to have very thin bars in the support, so that you can cut them very easily with any kind of tools, so you can remove the support easily. So the purpose of those two examples, the example 1 here and the example 2, is just to show you that the interface between the support and the structure that you want to build is very complicated. It's made on purpose. Either you have a tree structure or you have a dotted line of small holes for easing the separation of the support from the structure. So if you want to predict the effect of supports by doing some finite element simulation, it will require a very fine mesh, but you don't care about all the details. So what you want to do is, in some sense, do some kind of homogenization purposes, some kind of homogenization process, because you want to go very quickly in the simulation of those supports. So actually, what we are going to do is to model this kind of detailed interface between the support and the structure by a model of imperfect interface. Okay, so I'm not doing any homogenization here. I assume that the details of the small branching of the supports close to the structure will be represented by an imperfect interface. And I will explain this model of imperfect interface first in the case of thermal diffusion, and then later on in the case of mechanical system. Good. So now let me forget about the motivation for the moment, and let me consider a domain where you have two phases which are occupying two subdomains, omega-1 and omega-2. And those two subdomains are separated by an interface gamma. So there are two possible configurations. The first and simple one is when omega-1 is an island inside omega-2, and then gamma, the interface, is a closed surface, okay, or a closed line in the plane. And the second configuration, which is actually more relevant, but a little bit more complicated, is when the total domain, which is a union on omega-1 and omega-2, is cut in two pieces or several pieces by the interface gamma. So that means that the interface gamma is not a closed surface, but the interface gamma touches the boundary of the exterior boundary of the total domain. Okay. So now the model will be that this interface gamma is imperfect, meaning that the temperature in this thermal conduction model will be discontinuous through the interface gamma. But the normal heat flux, of course, is continuous by conservation of energy. And this normal heat flux will be proportional to the jump of temperature, like a Fourier boundary condition, if you want. So the complete model is here. So the temperature will be called U, Okay, it is made of two functions, U1 in omega 1 and U2 in omega 2. And I introduce the characteristic function chi1 for omega 1. So it's 1 in omega 1 and 0 outside, and chi2, which is 1 inside omega 2 and 0 outside. Okay, and so the temperature is made of two functions which are not continuous at the interface gamma. So in every subdomain omega I, you solve the heat equation with some constant thermal conductivity AI, with a given source term F. So the source term F is globally defined over the union of omega 1 and omega 2. And at the interface gamma between the two subdomains, you have continuity of the heat flux, normal heat flux. And then this normal heat flux is proportional with a constant of proportionality that I call alpha to the jump U2 minus U1. Okay, and alpha is positive because I choose the orientation U1 outside from omega 1, and so the jump is U2 minus U1. So the convention of the jump between U2 and U1 and the normal U1 is the right one, so that you get alpha that can be interpreted as a conductance of the interface. The inverse of alpha is a resistance, a thermal resistance of the interface. And then usual boundary condition on the exterior boundary of the domain that I call capital D, which is omega 1 union omega 2. Of course, when alpha is plus infinity, that will force U2 to be equal to U1 on the interface, and then you recover the classical transmission condition at an interface. But then, if alpha has a finite value, this is an imperfect interface. The temperature is not continuous, and you have some resistance, thermal resistance, which is the inverse of alpha at the interface. Good. So of course, this is a very standard model. You can find it in many places in the literature. And then you have a standard variational formulation, which is the sum of the two variational formulation in omega 1 and omega 2. Then at the interface gamma, you have a bilinear form that involves the product of the jump of the unknown u and the jump of the test function. And both the unknown u and the test function v belongs to space H1b, B for broken. That means that this is a set of function u in L2 of the global domain capital D, and the restriction to omega 1 belongs to H1 of omega 1. The restriction to omega 2 belongs to H1 of omega 2, but there is no continuity of the function u1 and u2 at the interface gamma. So existence of uniqueness is really very classical for this model. Good. And then, of course, the goal is to do some optimization. So the shape is not the variable of optimization. The shape, the interface gamma is the variable of optimization. So actually, I will denote by j of gamma an objective function, which generally speaking could be an integral over the complete domain capital D of j, small j of u, the solution of the state equation, plus an integral carried by the Neumann boundary condition of another function k of u. Small j and small k are smooth functions with some growth at infinity, so that this is well defined. And the problem is to minimize this objective function among all admissible interfaces. Gamma belongs to a set of admissible interfaces with a volume constraint, let's say on one of the phase, let's say omega 1. Okay, good. So it's a very classical optimization problem. And what we want to do is, I don't want to say anything about existence nor uniqueness of solution. I just want to devise a numerical method to do some optimization. And the first goal is to compute a shape derivative, a derivative with respect to the position of the interface. So in the setting of Hadamard, you introduce a displacement vector theta, and you look at perturbation gamma index theta, which are obtained by applying the map identity plus theta, meaning that every point x in gamma is displaced to a new position x plus theta of x, and differentiating in the sense of Hadamard is differentiating with respect to this displacement vector field theta. Okay, so you said that the function j of gamma is shape differentiable. Actually, if j of gamma index theta is differentiable with respect to theta. What does that mean, Fréchet differentiable? Well, you build this first order Taylor expansion where the remainder term is small with respect to theta in the W1 infinity norm. So very classical setting. Good. So when we compute this shape derivative or derivative with respect to the position of the interface, we need an adjoint state, and the adjoint state is very classical. I call it P. It satisfies the same type of equation, except that you replace the source term by the derivative of the integrand of the objective function, so minus j prime of ui. You still have the continuity of the normal influx. You have the same interface, imperfect interface boundary condition for the adjoint. So the normal heat flux is proportional to the jump of the temperature. And again, because I had one part of the objective function which was carried by gamma n, you have a non-homogeneous Neumann boundary condition on gamma n that depends on k prime of u. So in the sequel, I will always implicitly assume that gamma is smooth enough and that U1, P1, and U2, P2 belongs to H2 in each subdomain. Of course, they are not in H2 globally because they are discontinuous at the interface, but in each subdomain, they belong to H2 so that everything has a meaning when I will compute the shape derivative. And then I have a theorem that gives you the shape derivative. Please don't look at the formula. The formula is absolutely awful. It has absolutely no interest except that I needed to use it in a numerical algorithm. But I just want to tell you that also this formula is awful. To prove it is not very hard, actually. The formula involves jump through the interface, okay? So you have three terms in this formula. The first term is carried by the interface. So that's a classical term that you will expect, okay? And it depends only on the normal component. Nu is a normal to this interface gamma. It depends only on the normal component of the displacement vector. So that's the usual part. And then you have two additional parts which do not exist if gamma is a closed surface. So if gamma is a closed surface, you only have the first term. But now if gamma touches the boundary of the domain capital D, then when gamma moves, you move also the touching point on the boundary. And so you need to take into account that. And then you have two terms, one where you see the tangent vector tau, and another one where you see another tangent vector t, which is not tau. Okay, so tau is tangent to gamma, to the surface gamma, and it's also normal to this boundary of this surface gamma, which is not closed. Okay, now t is different. T is tangent to the boundary of the domain capital D, and it is normal to the boundary of gamma, but it's not tangent to gamma. Okay, so it's a little bit complicated. If I come back to my picture of this setting here, you have one which is tau, which is tangent to the surface gamma or to the line gamma, if you want here. On T is a tangent to the boundary of the global domain capital D. Okay, so that's two different integral terms if gamma is not a closed surface. Good. So the proof, the formula is awful, but the proof is very simple because actually, in the case of the perfect interface, the proof will be more delicate because you have the transmission condition to take into account. Here, the transmission condition, you have no transmission condition because the temperature has a jump. So actually, there is no transmission boundary condition. You just write the variational formulation, you add the objective function, and you just use the standard method proposed by CA to differentiate this Lagrangian to find the shape derivative. So actually, the proof is really simple. And the fact that on the boundary terms, you get two different unit vectors is that because you get two different terms which are differentiated on the boundary, one which comes because you differentiate an integral which is in the fixed boundary gamma n, and another one that comes because you differentiate something which is on the integral of gamma, and when gamma moves, you have a component at the endpoint of gamma. Okay, so I don't want to enter into the details, but actually the proof is simpler than in the case of a standard interface condition. Okay, so now we have a shape derivative. So we can do, we can devise an algorithm to do optimization, shape optimization, and there will be 4 ingredients in my algorithmic implementation of this optimization algorithm. First, because I'm moving an interface, I need to, have a method for that. I'm using no surprise, the level set method for advecting the interface. Now, in my motivation, what happened at the interface is really very important. So I'm going to require that the interface is exactly mesh, so my computation will be very precise. In particular, I have something which is discontinuous at the interface, so I want really to compute exactly what happened at the interface. So I'm going to remesh at every iteration of my optimization algorithm. I will remesh the entire domain so that the interface is exactly captured by the mesh. And for that, I'm using a free software which is called MMG. It was developed by the team of Pascal Frey in Jussieu and my former PhD student, Charles Daponi. Then there is a small trick for the finite element computation that I will explain, and the finite element computation are done with FreeFM++, also developed at Jussieu. And then for the optimization, I use an augmented Lagrangian algorithm because I remember there is a constraint on the volume, so this constraint is taken into account by an augmented Lagrangian algorithm. Excellent. So the level set method, I guess you know that. Here is a picture. The interface is this difference between the light gray and the dark gray. And by definition, the level set is 0 on the interface, negative, let's say in omega 1, and positive in omega 2. And if the interface moves with normal velocity capital V, a scalar function, the equation for psi is simply d psi over dt plus v modulus of nablab psi equal to 0. But how do you guess this velocity v? Well, you use the shape gradient that you have just computed. And so there is two cases. When gamma is a closed surface not touching the boundary of the domain capital D, then that's easy because the derivative that I have computed is something like an integral over gamma of theta dot n, the normal component of my vector field, n is a normal vector to gamma, times some integrand j that depends on the state u, on the adjoint p that I have introduced. And so you see that if you want to choose theta such that this integral is negative, that means I will go in a direction that minimizes a function capital J. One simple choice will be simply to say that the normal velocity v is exactly theta dot n, and you choose theta dot n to be equal to minus j, which guarantees that the derivatives, the directional derivative, will be negative. Okay. Then it's a little bit more delicate when gamma touch the boundary of the global domain capital D, because in the shape derivative you have terms which are not carried by an integral on gamma, but which are carried, if we are in 3D, on a line, which is the intersection of gamma with the boundary. So then, not only the normal velocity plays a role, you have a normal velocity, but you also have a tangential velocity. And even more than that, you have two different tangential velocities because there were two different tangent vectors. So what we do is instead we compute a vectorial velocity, vec v, you see a v with a small arrow here, and I use a scalar product for some Hilbert space. So in theory, I should choose an Hilbert space, for example, H2, okay, for which I'm sure that in 3D, I have a notion of trace on surfaces and on lines, right? But actually, in numerical practice, I just use a scalar product of H1, and I'm cheating a little bit. So, I'm saying that I have a trace on the line, which is not true for the continuous space, but you can always do that in finite elements. But in some sense, you need to use a small trick to extend your velocity, because your velocity is not only a normal velocity, but also a tangential velocity. I do not go to the details, but you can imagine there are some technical details at this point here. Now, what about the finite implementation? I mean, usually people use standard continuous finite elements, right? And here on the interface, the temperature is discontinuous. So either you go to Galerkin discontinuous finite element, but if you are using a usual package, maybe you don't have discontinuous finite elements. So if you use continuous finite element, here is a small trick. Actually, you introduce two fields, u tilde 1 and u tilde 2, okay, that are computed everywhere in capital D. So usually u1 is restricted to omega 1 and u2 is restricted to omega 2, but here you compute them everywhere. So I wrote the variational formulation where I replace u1 by u tilde 1 and u2 by u tilde 2, right? And the same for the test function. But of course, U1 and U2 appears only in omega 1 and omega 2. And if you want to have a rigidity matrix coming from the finite element, which is invertible, you need to extend it. But no need to extend the bilinear form with a derivative. You just add, for example, U tilde V tilde 2 in omega 1, U tilde 1, V tilde 1 in omega 2, and you put a small parameter epsilon. Epsilon does not need to be very small. 10 to the minus 5 typically will do the job. And then you reconstruct the temperature U by taking U tilde 1 in omega 1, U tilde 2 in omega 2. You're making an error of size epsilon, but epsilon is small enough. And you see it's enough. And of course, there is no continuity of U tilde 1 and U tilde 2 at gamma. So for sure, you don't have continuity. Well, if you were using standard finite element, you will have the continuity built in. So you cannot do that. So that's a way of doing it with standard finite elements. Okay, so let me show you some examples. And let me start with a very classical example, which is a so-called radiator. So it's a square domain here. You have a unit heat flux on the upper boundary here. At the two lower corners, you see the dashed line here. You have a cold end, that is a Dirichlet, homogeneous Dirichlet boundary condition. All other boundaries are adiabatic, that is homogeneous Neumann boundary condition, and there is no source term inside. So more or less, you're putting temperature, heat flux, if you want, at the top, and the heat can be extracted by the two lower corners, and you mix a good conductor, A2, which has conductivity 1, and a bad conductor, A1, which has conductivity 0.01. And what you want to minimize is so-called thermal compliance, so that the integral on the top boundary gamma n of the heat flux that you impose, which is 1, multiplied by the temperature. Okay, so that's equivalent to the thermal store energy inside your square domain D. And you want to minimize this with a volume constraint of 50% for each conductor. So you want to get, in some sense, the best arrangement of the two phases so that you dissipate thermal energy as much as possible. So here is the solution that you obtain with a perfect interface. So I have an initialization. The good conductor is the white phase. The dark phase is the bad conductor. And you see that starting from this initialization, what you get is some kind of fibers of the good conductors that comes from the top and brings the heat to the two lower corners where the heat can escape. Okay, so that's the optimal radiator in some sense. So this was done with a perfect interface, so continuity of the temperature. Now, what do you obtain? Just to tell you how well it converges. You see, because I started with a configuration which has not the right volume, it takes some time that you convert to the right volume, and the cost, that is the thermal compliance, is minimized in the end. But of course, it first increase because you first reach the correct volume, and so when you have more good conductor, the thermal compliance will be smaller. So everything is smooth in the conversions. That's what is important to see. Now let's see what you get with an imperfect interface. The perfect interface is still on the left, and on the right you see the imperfect interface with a conductance of 1. But actually, if I had put any other value of alpha, you will get almost the same topology, the same shape. Okay, so this is a very deceiving example. Just want to show you one case where changing the value of alpha, going from a perfect interface to an imperfect interface, does not change the design. But of course, all the coming result will show you that in the other cases, there will be a difference between a perfect and an imperfect interface. So let me come to another very classical test case, which is a so-called heat extraction test case. Again, my domain is a unit square. I have a bulk source term F equal to 10 everywhere. All boundaries are adiabatic, that is homogeneous Neumann, except a very small part of the bottom boundary at the bottom where you have a homogeneous Dirichlet boundary condition. So again, you mix two conductors, A1, which is a good conductor, A2, which is a bad conductor. And so you want to minimize the so-called thermal compliance, because I have a constant source term. So this function J of gamma is exactly the equivalent of the thermal compliance or the thermal store energy in the domain. You want to minimize it. That is, you want to find the best configuration of the two phases so that heat is extracted as much as possible. Again, this is a self-adjoint problem, and I have a volume constraint, so I have only 20% of the good conductor and 80% of the bad conductor. So here are three optimal design obtained with our algorithm. On the left, it's alpha equal to plus infinity, meaning perfect interface. In the middle, alpha equal to 1, and in the right, alpha equal to 0.1. So that means that going from left to right, the interface is more and more imperfect. The resistance of the interface is bigger and bigger. And so you see that the design are different. And actually, you see that when the resistance of the interface is large, you want to have an interface which is with a smaller area. And actually, if you compute the length, because we are in 2D of the interface, on the left, the length is 12. In the middle, it's something like 6. And on the right, it's a little bit less than 6. So the length of the interface is decreasing because you pay a cost of the interface resistance when you minimize the thermal compliance. So increasing the resistance of the interface means that you want to decrease the length of the interface, but still, you still want to have, kind of branches, because a good conductor, which is a white one here, carries away the heat produced by the source term up to the exit, the cold end, which is a small Dirichlet boundary condition at the bottom. So you see a very important role of the imperfect interface in the optimal design if you change the value of alpha. So now that I have explained all the details in the thermal case, let me go to the mechanical case, and let me slightly change the setting, right? Because in the mechanical setting, my two phases are actually two different structures. Omega is a structure that you want to build. In my picture, it's a red structure. You recognize a cantilever structure, which is a classical test case in topology optimization. So I want to build this red structure. And then the other phase is a so-called support that I call S, like support, which are in blue. And those supports are supposed to support the parts of this red structure, which are almost horizontal, because remember, I told you that in additive manufacturing, it's hard to build things which are close to horizontal. So you see that those blue supports support more or less the almost horizontal part of my red structure. So what are the slight change? Before, in the thermal case, I was optimizing the interface. But actually here, I don't want to touch to the red structure. Omega is fixed. Okay, so omega is fixed, meaning that the interface is sliding or moving tangentially on the boundary of my fixed structure, small omega. Okay, so actually the optimization variable is rather S than gamma. Gamma, if you want, is the intersection of the boundary of S and the boundary of small omega. But gamma is must be carried by d omega by definition, because the support omega. So actually, I'm not moving normally gamma. I'm just moving tangentially. So it's a bit different. And then in the previous case, I showed you an example where the thermal conduction was different in the two subdomains. Here, I'm building the support with the same type of material. So actually, the material parameters are the same between omega and S. I will not play with different material parameters. I could, but I'm not going to do that for practical reasons. So omega and S are made with the same material. Okay. But still, there are some ideas. In particular, I still have a model with an imperfect interface. So I'm solving minus divergence sigma of u. Sigma of u is a stress tensor equal to F some applied load in both small omega and S separately. Sigma of u is a usual stress tensor, so it's computed from the strain tensor E of u. E of u is a symmetrized gradient. U is a vector valued unknown, which is a displacement. And I have the Lamé parameters mu and lambda as usual. Then on some part of the the structure gamma d, on the boundary of the structure gamma d, the structure is clumped, so u is equal to 0. Typically, that will be at the bottom of my structure because I have the base plate and I'm building vertically my structure. On the other boundaries of the global domain, I have a Neumann homogeneous boundary condition. And then on the interface between the support and the structure, I have continuity of the normal stress tensor. So the jump of sigma u times nu, the normal vector, is 0. But I have a jump in the displacement vector. And so the jump in the displacement vector is equal to some matrix capital R times the vector, which is obtained by sigma u times nu, the normal. Okay, and this matrix R is a compliance or the inverse of the rigidity of the interface, and it is characterized by two coefficients, alpha and beta. You have beta, which is compliance in the normal direction, nu is a normal vector, and you have alpha, which is the compliance in the tangential direction. So, of course, it's isotropic in the tangential direction. There is no reason to have something anisotropic, but it could be not isotropic between normal direction and tangential direction. So I have two numbers, alpha and beta, which are like inverse Lamé tensor, if you want, Lamé coefficient, sorry. So the inverse of alpha and beta are rigidities associated to the interface. Okay, so again, imperfect interfaces on the boundary. So again, this is a standard model of imperfect interfaces in mechanics. So I'm going to minimize the compliance. So I'm not looking at any objective function. That's the compliance that I'm looking at, right? And I'm minimizing for supports that belongs to a fixed box capital D, where of course you have the structure small omega, which is there. So the support cannot overlap on the structure. So the supports must belong to D minus small omega. And I have a volume constraint on the support because I don't want to use too much material to build my support. So remember, that gamma, the interface in some sense is constrained to belong to the boundary of my structure. So actually it does not move freely. So in some sense, the real design variable is capital S. It's not really the interface gamma. So again, you can compute a shape derivative. I skip all details because you've seen some details in the thermal case. And what is really important is that now there is, in some sense, a third phase. I didn't say that. There is a kind of a third phase, this white phase here, which is void. You have the capital D is my rectangle, small omega is the red part, the support S is the blue, and then you have voids among what remains, which is not support outside from the structure small omega. So actually, when you move the support, when you deform the support, you still have on the boundary of the support, but not on the boundary of the structure, a normal component of my vector field theta, and then you have something, okay, which is a derivative of the compliance objective function. And of course, at the endpoints, in 2D or at the line, which are the boundary of the interface between the supports and the structure. So it's a line in 3D, it's points in 2D. You have some terms that come from the imperfect interface term. And so you see that that's a tangential component of the vector theta that plays a role, where tau, again, is a tangent vector to the boundary of omega, but also normal to the line, which is the boundary of my interface gamma. Okay, so a little bit delicate. You move away from the structure, you move the support in the normal direction, but when the support touch the structure, you move it tangentially, not normally. Good. So let me show you some example, and that's a very classical standard test case, which is called the so-called M structure. So this is a light blue. That's my structure. That's an M. So why is it a standard test case? Because you have this corner here, which is for sure an overhang part. I mean, you have this corner. I mean, if you want to build it, you do it layer by layer. And when you have a layer that touch it, you will have to create an island of solid metal that will only touch the border behind. So it will, like a metallic stone, it will in water, it will go deep inside the sea of powder, and so you will not be able to build this structure if you build it layer by layer starting from the bottom. So of course it's a test case because it is impossible to build these small corners, reentrant corner, if you do not have support. So I have my light blue structure, which is fixed, and then I have my initialization of support in dark blue with some holes inside, and I want to build the support that minimize the compliance for which load? Well, for gravity load, because actually that's exactly what happens. I mean, the gravity is applied to my melted structure, and it will go down inside the powder because of gravity load. So I'm minimizing compliance for gravity load, and I'm trying to optimize the support to minimize this with a volume constraint on the support, which is 1. So something you will see on the structure how it goes. So here are the support that I obtained for this M structure. So on the left, I take very small value of alpha and beta, which means very large rigidity of my interface. So what does that mean? That means it's almost a perfect interface. Okay, that's the limit case of a perfect interface, if you want, on the left. And you see that the supports are more or less vertical bars supporting the M, but those vertical bars are very thick, close to the reentrant corner of the M. Now, if you decrease the rigidity of the interface, so alpha equal to beta equal to 20 in the middle and 50 on the right, you see that you need more and more support, because the contact between the support and the structure is not good. So you need to thicken the support, and the support get closer, if you want, to the lower corner here. So no big surprise in some sense. But what is really interesting is then when you vary the rigidity in the tangential and the vertical direction. So here, on the left, you still have the perfect interface case. In the right, I choose values of alpha which are larger than beta. So that means that the rigidity in the tangential direction is weaker. So that means that, in some sense, the support is sliding along the structure. And what you see in the extreme case on the right, where alpha is 5 times larger than beta, so that means that really the support works only the normal direction. It's very weak in the tangential direction. Well, the supports have a tendency to be normal to the structure, to be efficient. Okay, so that's exactly the kind of thing that we would like to see. And of course, if you do the reverse case, which is to have a normally weak interface, what you see on the right, which is an extreme case when the interface is very weak in the normal direction, but very strong in the tangential direction, you see that the support acts more or less tangentially. So they do what we want them to do in some sense. And then it's very interesting to see, because if you take a different structure, let's take a triangle, right? So that my light blue is a structure that I want to build. That's a triangle. If you do the perfect interface case, you see that, of course, because you want to build layer by layer, horizontal layer in the vertical direction, you see that the support are mostly vertical. But then if you have a weak interface, then you see, by the way, here the support can be attached to the bottom side, but also to the lateral side, but not to the upper side. And then you see that if you have a weak interface, then it becomes advantageous to have supports that are also coming from the lateral side. And that's something which is used by engineers, by the way. Even if you build layer by layer from the bottom side, sometimes they build a vertical layer, and then they have support starting from this vertical layer. So we were very happy to see by your optimization algorithm that indeed it is a good strategy if you can build a vertical layer to have supports which are attached to the lateral boundaries and not only to the bottom boundaries. Okay, so a very complicated structure which is not intuitive, and of course with a topology which is completely different with the topology that you could get with a perfect interface. So of course it works in 3D, and because time is running out, I'm just going to show you one example. Again, it's a classical test case. You see only here on the left 1/4 of the test case. It's a table, it's a circular table with just one pillar at the bottom, and you want to build support for it, because of course it's an overhang, it's an horizontal structure on most part of it. And so you see the type of support which are non-conventional in the sense that, of course, the support comes from the base plate and the support from behind, but there's also support from above, because the interface is not perfect. So it's better not only to put support from below, but also to have some support from above. And so we have a very complicated structure of support in this case. And if I use supports which are normally weak, so they are strong in the tangential direction, but weak in the normal direction, we see something kind of strange. You see it tries to clump the table at the boundary of the table in order to act in some sense horizontally, so that is tangentially rather than vertically. So we have a very different support if the interface is perfect according to the different rigidities in the different direction. So conclusion, what we wanted to prove is that if we take into account the fact that those supports are pre-cut, in some sense, you have dotted holes close to the interface with the structure. If you take that into account, maybe the topology and the shape of the support will be very different, and that we have been able to prove. What we should do is actually to have maybe some kind of a different rigidity if you are in traction or compression. You could expect that probably it's very stiff under compression, but not very stiff under traction. And actually, traction can happen because here I showed you examples with only gravity loads, but actually you can compute so-called equivalent thermal forces that comes from the thermal residual stress. So you simulate the fabrication process where you have a thermal and elastic model, so a thermoelastic model. You compute the deformations, the thermal residual stresses, you deduce from them equivalent thermal forces, and then you do the optimization for those forces rather than for the gravity forces. And they typically give you more traction loads rather than compression loads. Of course, you could do multiple loads or multiple states because, if you say, well, why do you use thermal forces rather than gravity forces? Well, you could do both, actually, and that could be explored. And then, of course, in the end, you've seen that I've shown you some pictures. I'm working with people that are doing experiments, so we should do real experiment to see if those supports for imperfect interface do perform better than the classical ones. And let me conclude by wishing a very happy birthday to Enrique.
So many thanks, Gregoire, for this very interesting talk. And okay, so now we can hear some questions, comment, and start discussions on this subject. So the microphones are opened and the written chat, it is also open.
So Carlos, can I ask some?
Yes, yes, of course.
So merci, Greg. So thank you, Greg. Is in the problems you consider the right-hand side F was always fixed and given?
Yes.
Yeah. So.
Yes. And typically, yeah, it was continuous through the interface. Now if you were for example, when I talking about gravity loads, gravity is the same for everybody, right? But the force will be the material density times the gravity. And so here, in the case of metallic additive manufacturing, we are lucky that the material parameters are the same. So that means that the gravity forces are the same in the structure and the support. And so there will be no change in the force when you move the interface. Where you could look at least from a mathematical point of view, to a case when the force will be discontinuous. You will have one force in one domain and another force in the other domain. And then there will be another term in the derivative.
Yeah, but so it would not be natural to also consider the case where, other than, for instance, the gravity force, you add a force applied by some other, I don't know, for instance, an object you are posing on the surface of the table?
Yes. So that's exactly what I call equivalent thermal forces. So actually, I'm doing this with, because I mean, gravity forces is good because they prevent or they have a tendency to produce support to support the horizontal part of the structure. But actually, when you have horizontal parts, not only you have this problem that when you build it, it will be supported by nothing, you don't have support, but also when you build it after, after the end of the process, the amount of heat that you have released to melt it leads to thermal residual stresses, and then you have bending because of those thermal residual stresses. So in the end, when you remove the powder, your structure is not flat, but it's bended by those thermal residual stresses. So you want also to avoid this. And so you could have supports to avoid this. And then you need to avoid this to put not gravity forces, but those equivalent thermal forces, which have been pre-computed by your computation of the building process for your structure without any support. So yes, there are various recipes in some sense of different forces to have the right support for your structure.
Mm-hmm. Thank you.
Thank you. So, Greg, I also have a question in the same line as Enrique. Your target seems to be always the minimization of the compliance, okay? Or you can change your force by these equivalent thermal forces. But what about the eigenvalue associated to the structure? For example, to minimize the first eigenvalue.
Okay, so very good question. Let me ask the first part of the question. Let me answer the first part of the question, which was, I'm using compliance. And indeed, in my talk here, there was only compliance. But in real life, we are using other objective function. So there are two other objective functions which are very classical. First one is you want to minimize those famous thermal residual stresses. So you have a measure, for example, of the L2 norm of the stress, and you want to minimize this L2 norm of the stress. Another one is you want to avoid deformation, so you minimize the vertical displacement, so that in the end, your structure will not be deformed thanks to the action of the support. Okay, good. So that's used, and then you need to use an adjoint, and I didn't show any computation with that, but that's something that we do classically. Now you talk about eigenvalue and eigenfunction, and here that's something that you could use to optimize your structure, because, for example, your structure could be submitted to vibration, and you want to minimize or to maximize rather its fundamental frequency. So that's a standard optimal objective function for the final use of the structure. But during the building process, and that's during the building process that you need the support, I don't know of any eigenvalue problem which is relevant.
Okay.
You see, eigenvalue and eigenfunction are okay for the final structure, but during the building process, I've never seen any objective function linked to the eigenvalue of the eigenvectors.
Okay, I understand. We have two hand raised, Martin Lasert and Giuseppe Butazzo. So we can start by Martin.
Okay. Hello, Greg. Thanks for the nice talk. I have a follow-up question. So usually when someone deals with optimal design of two materials, the problem is not well posed and you have to relax it, in the sense that you allow for regions consisting of fine mixture of two materials, rather than just have two separate regions, each one consisting just of one material. So is that a case in your problem as well, or you don't need any kind of relaxation?
You are absolutely right. I said I would not say anything about existence and uniqueness, but you're right. You would expect a relaxation phenomena by mixing two phases, right? The relaxation will be a bit more delicate because I have an interfacial term. And so you don't expect to have very fine mixtures, because if you have very fine mixture, the term in the variational formulation, which involves the interfacial energy in some sense, will blow up. I mean, if you have very small inclusion, maybe the total volume is bounded, but the interfacial energy may blow up. So, you know, it's not clear how you will relax this term. I suspect still we will have an homogenization phenomena, but it's a little bit more complicated than the standard homogenization phenomena that we know. So if you want to avoid this, you know, I said that the interface must belong to some set of admissible interfaces. Let me just add a uniform bound, for example, on the curvature of my interface. You know, something is the spirit of the work of Denis Chenet. So if I have some uniform bound on the mean curvature, for example, you have some compactness, and then you have no relaxation phenomena. But of course, if you forget this bound, you will have a relaxation phenomena and probably an homogenization result.
Okay, but does the functional consider attains its infimum or not?
No, that I don't know. That I don't know. Very good question. I don't know.
Okay.
There was some work. There was some work by Rob Lipton on this, maybe Lipton and also Bogdan Vernescu, that were looking at a property of composite materials with imperfect interfaces. And I don't remember exactly what were their final result on this. That's a good point.
Okay, thank you.
Okay, thanks, Martin. So, Giuseppe, you can ask your questions.
Hi, Grégoire.
Hello,
so, concerning the comment you did in the last slide about different rigidities for traction and compression, one could expect that very thin bars could produce a lot of buckling. So do you think reasonable to impose an extra constraint about the thickness? So you only allow bars which have a certain minimal thickness.
Very good question. Thank you. Of course, this is linearized elasticity, so no buckling is taken into account, and that's a default. I agree. Now, my point here, you know, I'm replacing a precise description of the small details of the support close to the interface by a very rough model of a weak interface. So I'm not going to go, you know, with this very rough model to a very precise mechanical model, because that will make no sense. I mean, you know, I'm making a very large, very big assumption by replacing the details of the geometry by my imperfect interface condition. So if now I go to a very precise mechanical model, that doesn't make any sense. But you're right that instead of taking into account a buckling constraint, I could put a thickness constraint, and that I know how to do that in previous work that I did. And that's a classical issue. You know, you could have a constraint on the minimal thickness for the support. And then you could expect that this minimal thickness could be tuned so that it will not buckle. That's possible, yes.
Okay, thanks.
Okay, so thank you very much again, Greg, for this very nice talk. And we can thank him again. And now let's go to a brief break, a coffee break. So you can have your coffee at home or at the office. And we will stop for, I don't know, some 10 or 12 minutes. And we will come back in here in Chile at 11:40. And in Europe, 4 hours plus, so 15:40. Okay.
Good.
Okay, so
thank you.
You can
see you. Thank you.
See you in 12 minutes.